Today we're going to be looking at preparing ourselves for a lab um, that we will perform in the class. Okay, so the lab is we're going to analyze a hydrate, and what we're going to do is we're going to add heat to it using a Bunsen burner, and we're going to evaporate off the water, okay, within its structure. So a hydrate, which does a review. So basically, we're looking at an ionic compound here that it will incorporate some water molecules into its structure. Okay, so when you're looking at a hydrate versus something that isn't hydrated, an anhydrate, you'll see that they're actually different colors. Like they'll be kind of the same shade still, but the hydrate will be a lot more colorful, vivid, and so forth. And the hydrate will look just more of like a pale form of like if it's a blue color, really bright blue versus a very pale, almost white color. Okay, um, so so there's some examples here like gypsum. It has calcium sulfate as a solid, but it will incorporate ratio of two water molecules. Okay, so it'll be called calcium sulfate dihydrate. So we practice naming these. And so now we're going to just experiment with them as well today. Okay, so just a reminder, you put a dot in the formula, but you don't put it in the name. Okay, and then you use the prefix and you say hydrate instead of water. Okay, some other examples here are, lithium perchlorate, trihydrate, magnesium carbonate, pentahydrate, copper 2 sulfate, pentahydrate. Okay, that's the one we're going to study. Nickel 2 sulfate hexahydrate. Okay, and then the water in this hydrate compound is, they call it the water of hydration as well. And we're going to heat it with a Bunsen burner, and we can remove the water from the substance. Okay. All right. So when it has the water in it, it's called the hydrate, and when it doesn't, you say anhydrate. Okay, so here are some visual examples of an anhydrate and a hydrate. Okay, so we have cobalt 2 chloride here. When it's anhydrous, okay, without the water, it looks this color, and when it does have water within the structure, it has quite a big difference in the way it looks. Okay. All right, here's the one we're going to study, copper 2 sulfate. So this is the anhydrous version. So you see, it almost looks white, but light blue, pale blue to it. And then we have a copper 2 sulfate pentahydrate. This is where the water is in within the structure. Okay, so this is the the hydrated or hydrous. Yes. If you do heat this up and dry it out, and then leave it overnight, it does start to start absorbing the water out of the air again and start to get kind of its color again. Structurally, really quick, so you can see here, copper is the orange, sulfate is the yellow with the red here, and then the water is kind of attaching on. Okay, and then I don't know, try to find a simple one here where you don't have it on, the copper and the sulfate just come together. Okay. All right, so we're going to just do an example here as part of our pre-lab. So a pre-lab is something that you will have to do often when you go take chemistry, in future chemistry courses and a lot in post-secondary. Okay, so they want you to sometimes read up on some information, do some questions, get informed about what's going to happen in the lab. Maybe do some examples, and then you go in and do the lab, and then you should be able to complete the lab on your own. Okay. All right, so we're going to start off with this example of a barium chloride dihydrate. Okay, so we have a barium chloride hydrate compound that has the 2 water. So we're going to heat it up. So we're going to use a Bunsen burner and some various equipment to heat up the substance, and then we'll get the anhydrate or anhydrous sample. So we have barium chloride only, and then the 2 waters have evaporated off. Okay. All right, so from here, what we're going to do is we're going to look at some experimental data, and we're going to find, so here was a lot of wording here, but in the end, we're going to find, propose a formula, a hydrate formula. So basically, We're going to pretend we don't know how many water molecules are in the structure, per 1 barium chloride. And we're going to use the information that we found from our experiment to figure out what it should be. What's the ratio from barium chloride to water? Then we're going to find the percent composition of water, so how much water was evaporated off in the experiment, and how much water is actually in the hydrate sample theoretically, if it's a perfect world and the experiment goes well. Okay, and then since we're going to have an experimental percent composition and a perfect world composition where everything's perfect, the experiment goes perfectly, how much water will we have? We're going to have a difference in the numbers, and we're going to analyze, all right, it's down here, we're going to analyze the error in our results. Okay. All right, so let's start off with finding the hydrate formula. Okay, so what we're going to be doing here is we're going to be taking data that's been found experimentally, and then data that we should be able to figure out because we know the actual formula, and find out how much water there should be. Okay, so we have our experimental percent hydration and our theoretical percent hydration that we'll get to. But before that, I want you to guess the number of moles, so we'll do that first, okay? All right, so here, I'll just move this onto the page here. Okay, so we have, here's our data from our lab. So basically, we put our sample into the evaporating dish, okay? And again, you'll see in the lab what these all look like. So evaporating dish, and then we added the sample, about 4 to 5 grams. Oh, no, never mind. We added some sample. And then this is the mass that we got for the evaporating dish and the sample. We already took the mass of the empty evaporating dish, so then we could subtract it and figure out, okay, we are going to use 17.35 grams of sample, okay, of barium chloride. You're not going to use as much in the lab. It should be about 4 or 5 grams, okay? All right, from there, we are then going to heat the sample. And then when that's done and everything's been cooled down, make sure it is cooled down, okay? From there, we're going to take the difference. So say once it cools down, we found that both the sample and the sample after heating, so the dish and the sample after heating is 43.23 grams. We know what the mass of the empty dish was, so subtract those and we'll get our anhydrous sample mass. Okay, so basically if it was been thoroughly heated, how much will the sample weigh after the water has been evaporated off? Okay, so there is all the results. Okay, so step 1, I want you to propose a hydrate formula for from the experimental data. So basically, we're looking at it's barium chloride, and we're going to pretend we don't know how much water there is. So we're going to try to figure out what this ratio is. So 1 barium chloride to how many waters? That's what we're going to find, okay? And then just up here, I'm just going to write in, this is what we should get, okay? Because we already know from, the bottle or being provided this information. So we know that it's barium chloride dihydrate, okay? But right now, let's just take our experimental data and figure this out. So in order to do this, is similar to what you did with the empirical formula. You're trying to find the ratio between all the elements, but in this case here, we're going to find the ratio between barium chloride, one of these, to how many waters. Okay, so we can kind of set it up the same way. So we're going to go 1 barium chloride, okay? And we don't know how many waters, so let's do that. So what do we know? Let's take our mass information first. Okay, so barium chloride. Barium chloride. So basically, when we started off this experiment, we found the mass of barium chloride. So this is after we heated it and so forth. So this is the mass of barium chloride only, right? Like that. Okay, we evaporate off the water. So that is 14.79 grams. Okay, so we want to know how much water did we find experimentally was in the substance, right? So we find that by subtracting what we started with. So that's this here. And once we heated it, we were only left with this much. So we're just going to subtract, 17.35 minus the 14.79 grams, like that. Okay, so we're going to subtract those numbers, and we'll find how much water we need. Okay, so, or not how much water we need, but how much water was evaporated off. So we found that it's that much. Okay, so we have this mass to mass comparison that that we have here, but we can't make that comparison. Remember, things are different sizes. So in order to compare, just substances together, you want to go to moles. Okay, so that's what we're going to do next here. So barium chloride, again, that's how much we found was left over after heating. This is how much we figured out was evaporated off for water. So and we're not going to compare masses, we're going to use moles. But in order to get there, we need to divide by molar mass. Okay, so let's find the molar mass and then we'll find the moles. Okay, so from there, we found the molar mass here of water and barium chloride. Okay, so again, we're taking our experimental data, the masses of barium chloride and water, and we're making a comparison here. Okay, but again, we can't compare mass. We use molar mass to get to moles. And then again, this is the way that you can compare items in chemistry, right? You have to go to moles. Like how many dozens of things you have? Okay, now you can compare which one has more or less. All right, so we see that barium chloride has actually fewer moles, so a smaller amount of it. So we are going to use that and divide this number. And why do we divide this? Because I want to go, okay, if I had 1 barium chloride, right? So like I was saying here, if I had 1 barium chloride, how many waters will I have? I'm trying to figure out that ratio right now. So if I take these and compare them, you're going to find the mole ratio is, okay, so the first one will divide to 1, right? So that's 1 barium chloride. And then the other one, when you divide them up, so you'll get 2.0002.0009, like that, and it keeps going. But all right, so you can see that's a 1 to 2 ratio. Okay, so therefore you could say the hydrate formula, right? That's the one we're trying to propose, right? Is barium chloride with a dot with 2 H2O. So basically, for every 1 barium chloride, there's 2 water molecules in the hydrate structure. Okay, so again, we know that experiments sometimes, there are always things that happen, right? So if you don't get what it should actually be, don't stress. I want you to use your experimental data in order to figure out the correct, or just figure out some sort of formula that you can propose. And if it is wrong, it's okay, because I want to see that you know how to calculate using your data. Okay, and then when it's not correct, you can really have a good think about why isn't it correct? Why isn't it what it should be? Okay, what kind of errors happened during the lab? Okay, so I want you to start thinking about how did you maybe why are you not getting the right water sample? Why are you not getting maybe the right barium chloride result and so forth, okay? Or these masses here. All right, so now that that's done, the next part of this pre-lab and what you'll have to do for your actual lab is that you need to now, let's find the percent composition, okay? So we know that we found 2.56 grams of water. What percent is that of the actual barium chloride compound, okay? Or the actual hydrate compound. And then let's actually calculate out the actual percent that water should be in this barium chloride dihydrate compound, okay? All right, so let's go down here. So we found experimentally that we had a mass of 2.56 grams of water. Okay, so in the previous part of the lab, we kind of applied what we were learning with the empirical formula method, where we're trying to find the ratio of elements to other elements. But in our case, it was like how many barium chlorides to how many waters. Okay, so in this section here, you're going to use what you learned with percent composition. So you know the hydrated compound, the barium chloride with the dihydrate, had this mass here. Once we heated it, we found that there was only this mass left. So we figured out that the rest of it had to be the water that evaporated off, okay? All right, so we're gonna find the percent composition of water using this experimental data. Okay, so how much water was in this hydrate? Okay, so this was the total mass. This was how much water we determined experimentally has evaporated off. So we're just gonna compare them. 2.56 compared to 1735 grams, we're going to get 14.76%, like that. Okay, so of the dihydrate compound, water is composed of 2.56% of the whole compound. All right, so that's what we found experimentally. What should we have found? Okay, um, actually, so basically, you know the formula is this, okay? So what we're going to do here is we're going to compare the molar masses of water to barium chloride. So one barium chloride to 2 waters. Let's we're going to do it for the overall thing. Sorry, we're going to compare the 2 waters compared to the whole thing here. Okay, so the mass for 2 waters compared to the whole barium chloride dihydrate compound, and we're going to find the actual percent composition. Okay, so I quickly calculated the molar mass of all the little pieces here, barium chloride. So here's 1 barium, 2 chlorines, right? Because 2 times 35.45 makes 70.9 of the chlorine. Okay, in the water, there's 4 hydrogens, 2 oxygens. So altogether, it's a mass of 36.04 molar mass-wise. So now, if I'm finding the percent composition of water, and this is the total of everything, I'm going to take just the water, and I'm going to divide by the actual total, like the total molar mass. Okay, so why am I doing this? I'm trying to figure out, okay, theoretically, okay, this is what I should get for percent composition of water. Okay, so 36.04 divided by 244.27, and I'm getting 14.75%. Let's change the title here. It said actual, it should be theoretical. So theoretical, this is in a perfect world, this is what percent of water will be of this compound barium chloride dihydrate. Okay, so 14.75%. Here's our experimental data. We found that 2.56 grams was evaporated off from a 17.35 gram sample. So we figured out water was 14.76% of the actual compound. So very close, okay? So don't be hard on yourself when you do your lab if it's not this close, okay? If it's really far off, something really went wrong. But to get something this close is, it takes a really careful experimenting, okay? So from here, we're going to go to percent error. And one thing I want to clarify here is this will be absolute value. So basically, whatever number comes out of here, you can just treat it as positive, okay? Because sometimes you can get too much sample, sometimes you can not get enough sample, right? So in this case here, I'm noticing our results are going to be negative, so you will just override it. Theoretical is 75. So there's that. Our actual results are a little higher, okay? So we got more water found experimentally than theoretically what we should have, but that's okay. We're just gonna change this part here to a positive when it pops out, okay? All right, so that leads to a 0.01 difference at the top. That's going to be negative, but we're just going to change it to positive. Okay, because in the end, we're just looking for how much is it off by. Okay, so divided by that. So once we multiply this all out, we're going to get a very small, here I'm just going to write a few digits here, percentage, okay, of an error. So this is you can pat yourself on the back if you get a small error like this. So you did your best to run their lab carefully, and then you only had a really less than 1% error in the results. So that's very good, okay? But again, when you run your lab, expect a bigger difference in error, okay? All right, so and then from there, you're going to make a conclusion. What did you learn? What did you find from the lab? And then what did you find the proposed hydrate formula will be? And what the percent composition, percent error will be, okay? And then you need to discuss the possible errors. Where, when you're running the lab, be thinking about this. Where did you maybe struggle to make sure that things were accurate and that you weren't losing sample, or where did you maybe when you were running the lab, did you um, maybe possibly make an error so that you weren't evaporating enough water, or maybe you were adding water. Just kind of think about all the different things that, remember, human error and instrument error. Okay, you can always blame those things. So think about, and again, it's you running the lab the best to your abilities, and then there's still some things you can't control, right? I don't want you writing about things like, oh, I got pushed, or I dropped the sample and stuff like that, right? You want to talk about things that you can't control that are going to affect your results. Instrument error, same thing. So instruments always have a limit. The scales always have a limit. So talk about what could have led to errors in your results when it comes to using the instruments in your experiment. Okay, and then yeah, so just go through, use this pre-lab as a reference in order to calculate the actual values of your real lab.